We have Lara here in the room with me. Right
Hi,
there.
everyone.
Yes, aloha, Laura. Roger, can you introduce Laura to us?
Absolutely. Lara's going to introduce herself, in fact.
Sure.
Laura, yes.
So I'm Lara. I'm a postdoc at Johns Hopkins University, but I work very closely with Raja, and so I'm here observing tonight as well.
I'm going to type your name into the chat.
Sure.
Fantastic.
Yes, that is me.
Yes, yes. I believe we are going to connect tomorrow in town, so I look forward to that.
Yes, I look forward to seeing you then.
Fantastic. All right, I'm going to mute myself. I'll just be in the background, Raja. If you need anything, just reach out.
Okay, I'm going to share my screen. Actually, I haven't set up my instrument control stuff yet, so a moment and I'll do that. Trenton, I'm trying to put a face to the name. So tell me a little bit more about yourself. I know Jamaica mentioned we spoke at Astro Day. Tell me a bit more, please.
Hi. I've got my son here. This is Kavika. Let me see if I can unblur my background. Yeah, so we met y'all at Astro Day, and very excited to join y'all. So thank you for hosting us.
Thank you.
Yay, thank you.
Hi, hello. Yeah, I remember you very well now. I didn't remember your name from when we met, but now I have it. Okay, so we're sharing 4 of these screens. I will be sharing 4 of these screens just in a second. And one of the things you'll be hearing, Trenton and Rohit, and Trenton, I didn't catch your son's name one more time, please. One of the things you'll be hearing are the sounds that the telescope and various computers make. So it'll tell us when exposures finish, when it finishes reading out the detector, the silicon detector. You'll hear that because I've shared sound and video, or audio and video with you. So we're in the process of doing a sequence of exposures. You can see that sequence running over here. It says 1 of 3, 2 of 3, 3 of 3. Can you see my cursor by any chance?
Yes.
Okay, so it's finished the first, second, it's on the third, and the length of the exposure is 1200 seconds. So 20 minutes, of which it's finished 5, and it's counting up. You can see. Someone just joined, so let me just see who joined.
It's Jeff. Jeff, welcome. I believe we spoke with you at Astro Day today, Jeff.
You did, yeah.
Fantastic. Welcome.
Thank you.
Roger was just talking about the screens that he's sharing. Roger, could we maybe go over that really quickly again for Jeff so he's caught up?
Of course. And thanks, Brenton. Thanks for sharing Rebecca's name. Okay, so we have 4 screens that we use to control the telescope and the instrument. The instrument is the spectrograph we're using tonight. And I'm going to cycle through them. The first one is called Control 0. You'll see that written at the top of the screen. If you can see my cursor, you'll see that at the top. Just move this bar out of the way a little bit. Can you all see Control 0 at the top?
Yes.
Okay, great. This is Control 1. And I'm going to move this window around just a tad. Okay, Control 1. This is Control 2 now. And this one is called Tel status for telescope status. And so there are our 2 last names. Lara's last name, my last name. We are the observers for tonight. If this were a split night where we have the first half and someone else has the second half, then you'd see more names. Break it down like that. We call this the PIG, the Program Identification GUI. So last night we were on a split night. We had the first half of the night, other observers at the second half. So at the crossover point, after midnight, we changed from one program to another program. This program name that you see here, U034, if you can see my cursor, you see U034. This is, U stands for University of California, and this was the 34th proposal submitted for this current cycle, the second half of 2023. Ours was the 34th proposal. There might have been others, there was certainly 33 submitted before us and probably more than 33 after us. So some subset of those proposals were granted time on the telescope. We are fortunate to be one of those proposals. So program number is U034. And I know we often see 3 numerical digits. So I know the number of submitted proposals. It's not uncommon for that number to exceed 100. The telescope is scheduled on a 6-month basis. Every 6 months, there's this competition, peer-reviewed, which other astronomers look at these proposals and deem some more worthy than others of getting time on the telescope. But you're seeing so this window is about the telescope, and you're seeing a lot of things here. Actually, this is showing you, I believe it's showing you the temperature, and this is showing you the humidity. We want the temperature to be nice and low, and you'll see that the humidity to be nice and low. We want it to be a dry night. We don't want any fog building up or anything like that. So it's in a very safe zone. Anything above 80, we'd start to worry. And all these green circles, green symbols means that we are in a very comfortable place with regard to the formation of dew. PRI stands for primary mirror, SEC stands for secondary mirror, out for outside, and precipitation falls means it's not raining. These are wind speeds. To worry about that. If the wind speed is too high, we may have to shut down the telescope. So these are sort of weather-related meteorological information. Keck is the name of the telescope. Keck II is the second of the 2 Keck telescopes that we're using. That's this little window down here. Lots of information here. The window in the upper right is telling us where the telescope is pointed. This is like almost like a map of the Earth. You have longitude and latitude to determine the unique location of a city or town on the Earth's surface. In our case, we use something like longitude and latitude, except they're called right ascension, denoted by the Greek letter alpha, and declination, denoted by the Greek letter delta. And those 2 coordinates are for particular, every star in the sky has unique coordinates like that. And so we are pointed towards the Andromeda galaxy. Andromeda has a nickname of M31. You see that up here, M31. S, because we're looking at the southern part of the Andromeda disk. Andromeda's got a frisbee-shaped structure. We're looking at the southern part of that. Capital B means one of, we have, capital B means we are working at relatively blue wavelengths, short wavelengths. That's what the capital B is. And the lowercase e tells you that that's one of many such M31SB zones that we're going to study tonight or in the course of this observing run. We had a half night last night, like I said. We have all night tonight, and we have the first half of Monday night as well. So a total of 2 full nights, equivalent of 2 full nights, a half night, a full night, and another half night. Just a moment. I think Sunny is, okay, Sunny's not going to be able to make it today. Just going to let him know. Okay, any questions about what you're seeing here? There are lots of different sort of cryptic things written over here, like LSE, UT, base, current, offset. If you have any questions about any of those, happy to do my best to answer them. Why don't I open it up to questions for a bit, just about the screen, and we'll go to other screens after that. I need not be about the screen. Any questions at all? While I
So LSD is local sidereal time?
LST is local sidereal time. It's the coordinates of the star or galaxy or whatever, it's coordinates of the astronomical object that is at its highest point in the sky right now. And it's constantly changing. You'll see it's changing at those are in units of hours, minutes, seconds, 20 hours, 59 minutes, 0, 0, 8, 0, 9, 10 seconds. So the longitude coordinate of a star is measured in units of time. It runs from 0 to 24 hours. So it's like a full circle around the sky. And that's changing at 1 per second because as the Earth spins, what is overhead changes at that rate. You can see why the right ascension of why the longitude coordinate of a star is given in time, because it makes perfect sense. As the Earth rotates, it does a full rotation in 24 hours, it sweeps through the entire set of constellations.
Raja, we had a question on what is DEIMOS, and of course I put the link in the chat and said that it's the instrument being used tonight. Could you tell us a little bit more about DEIMOS?
Of course. Thank you. Yeah. So DEIMOS is the instrument being used. DEIMOS is the name of what we call an instrument. And I want to explain that briefly. So the way astronomy works, most of the time, there are very few exceptions to this. You have a mirror that's focusing light. In the case of a mirror, in the case of a night like tonight or the Keck telescope, it's focusing light, the normal light that the eye would be able to see. The telescope's shaped like a bowl. So when light rays hit it, parallel rays coming in from a distance, when they hit it, after bouncing off a bowl-shaped mirror, the light is now in a converging beam. It's in a cone, like coming to a point. After the light comes to focus in a point, what happens to it after that? The system of lenses, mirrors, prisms, gratings, the system of optical elements, silicon devices, the list of these elements that process the light after it's come to a focus collectively is referred to as the instrument. So you have the telescope focusing light, that focused light goes into an instrument, and the instrument we're using tonight is called DEIMOS. It stands for Deep Imaging Multi-Object Spectrograph. DE for deep, I for imaging, multi-object spectrograph. We get spectra, we take spectra, like we create very extended rainbows out of individual stars, but we do this for multiple stars at once. That's why multi-object spectrograph. A spectrograph is simply something that measures a spectrum, a rainbow, from each star. And you can actually see a field of stars here. Every one of these white dots is a star. Most of these stars are either in Andromeda or in the foreground in our Milky Way. The bright ones are likely to be in the foreground in the Milky Way. The faint ones are likely to be in Andromeda. And just by looking at a picture, we can't tell. That's why I say likely to be. But if we were to measure a spectrum and measure a velocity and other properties, we could pretty well nail down whether it's one or the other, whether it's a star in Andromeda or a star in the foreground in our own galaxy. And you'll see that in this, below this thing called MAGIQ, M-A-G-I-Q, it's not magic spelled in a normal way. IQ stands for image quality. This is an acronym, so A stands for acquisition, G stands for guiding, and image quality. So I forget what the M stands for now. But this is a system that we use to make sure that the telescope is pointed just right and it's properly compensating for the Earth's rotation. In fact, if you see this little square here, it's zoomed in on a star. It's making sure that that star, the image of that star, it keeps taking images every few seconds and makes sure that the bright spot, the set of set of pixels that are bright because of the star's light hitting it, that those are fixed in pixel coordinates to a fraction of a pixel. If the telescope starts to drift for some reason, that the image of that star would drift, its pixel coordinates would change, and there's a real-time constant correction being applied to prevent that from happening. Otherwise, the image would get smeared out right over time. Below this display, you can see that there is a table. There's an index column, 1, 2, 3, 4, 5. These are the different patches of sky we're going to look at tonight. Each one has a name, M31SB. Many of them start with M31SB. You'll see an SR. That means we're looking at the red half of the spectrum, not the blue half. Actually, we use B and R, but technically speaking, the B masks look at blue and red light. We use a particular kind of, it's called a grating, the way we split the light and how much of that lands on the silicon device. We look at blue and red light when it's a mask with a capital B in it, and we only look at red light when it's a mask with an R in it. So it would have been cumbersome to write B plus R for the names. We're just abbreviating that as B, and whereas the R really means we're looking at red light, the red part of this rainbow spectrum. Now, these are coordinates. So again, this is like a longitude. It says RA, that stands for right ascension. Dec stands for declination. This is like a latitude. And Andromeda's coordinates are very similar to this. So we're looking at different patches in Andromeda. Okay, someone just joined. Let me see who that is. Oh, Richard just joined, I think. And Emilio, you joined earlier. For those who've just joined, and Jeff, I know Jamaica said hello to you. If you want to take if you want me to pause for a minute for people to say who they are, you can also type it into the chat. We'd love that. You know, how you found out about this, and be great. So there are multiple sensors within DEIMOS. In fact, I'll show you a picture of that. There are 8 sensors, 1, 2, 3, 4. Each of these sensors is a silicon sensor. They have 2,000 pixels along X and 4,000 pixels along Y, 2K by 4K. So this is CCD sensor 1, 2, 3, 4, 5, 6, 7, 8, and you can see 5 has been malfunctioning off and on for the last 4 or 5 years. And unfortunately,
exposure complete.
It's malfunctioning right now. You can see that. So it's going to read out a new exposure now. You're going to allow. Go for it. Go for it. Lara's going to do stuff. I'm just going to make sure I won't touch the screen. Actually, should I just go to one of the? I won't move. I'll be here. So Lara's doing stuff over here. She's changing the.
Okay. Do you want to raise something to you guys though? Because I think now's probably a good time for it. Sure. Think there might be a small issue with the ACS actuator system with a sensor. So I think now would be a good time to try to address that because we're
DCD readout complete.
And that possibly improve image quality, maybe a little bit, maybe not. Okay. Yeah, I would like to address it. So just give me a few minutes because basically I'm going to pull this sensor out of the system.
So I don't know if everyone could hear, but Tony, he's on the summit of Maunakea. He is trying to troubleshoot something on the telescope. ACS is the active control system that keeps the mirror shape as precise as possible. So we're just standing by while Lara is changing, we are going to now point at a different patch of sky, different mask. We're getting ready for that.
Change it now.
So I'm not going to switch screens for now, focus on Zoom, because Lara's controlling the, she's using the cursor to move things around, change various elements. You see that she's changing something called the slit mask. You can see her cursor there. I think you can see her cursor, yeah. She's changed it from what was BE to BH. So H is a different patch of sky than E. And these are our designations and not like other astronomers call these patches of sky by the same name.
Trenton has a question in the chat, Raja. Is the cross correlation plot related to motion compensation on the mirror?
Is it related to what, sorry?
Is it related to motion compensation on the mirror?
Not of the mirror, but of the spectrograph. The cross correlation that you see going on here, the right half of the screen, it has to do with the fact that DEIMOS, the spectrograph, is a huge instrument. It's, a few meters in every direction. It's this cylindrical shaped metal instrument. And in order to compensate for the sky's rotation, it has to rotate continuously in order to keep the sky fixed in the frame of its silicon devices. So when it does that, of course, it's heavy, so its gravity vector is constantly changing. And this giant piece of metal can flex ever so slightly. It can, under its own weight, it can change its shape ever so slightly. And what that does is it changes the mapping from where light is entering this instrument. Remember, you said focused light enters the instrument. From there to where it lands on the silicon device, it can change that mapping. In other words, even though it's a star and we're measuring its spectrum, that spectrum can get smeared out on the silicon device because of this flexing. This system on the right corrects for that. It's FCS, stands for Flexure Compensation System. It uses a cross-correlation method indeed. And you're seeing the dots that it cross-correlates in the upper part of that frame. The white dots come from light fibers that have copper lamps that create those spots. So Tony is still troubleshooting a couple of things, and then we start the new exposure. I'll explain some more.
Raja,
Uh-huh.
I think that.
do you have a slit mask you could possibly show?
I'll do that.
This does look like a bit of it. So I'm going to slew now here and get you set up. Thank you.
This is a slit mask, Jamika.
Yes, I thought Trenton and Kavika, if they haven't seen a slit mask, they would be interested in seeing it and maybe knowing how it's used.
So this metal plate sits in the entrance to the spectrograph. So where focused light is entering the instrument, DEIMOS, the spectrograph, this plate or plates like this one Obviously the plates we're using tonight are not here with us in Waimea. They're up on the summit of Maunakea. So there's a particular metal plate, and that's what these letter number designations refer to. M31 SBH is a different metal plate than M31 SBE. So Lara just switched from one metal plate to the next. And each of these metal plates has cuts in them, as you could see, has slits cut into them. And each slit is cut at the location of a star in the sky. So when the telescope is pointed just right, there's a light of a different star shining through each of these cuts in the piece of metal. And that's how we obtain spectra of multiple stars at once. That's where the MOS, multi-object spectrograph part of it comes in.
Thank you.
Or I'm going to quickly switch to the slit mask alignment tool so people can see it. To make sure that the telescope is pointed exactly right before we spend an hour collecting spectra of this patch of the sky.
Exposure complete.
When you have time, Raja, we have a question from Rohit. Rohit asks, how much of the southern disk of Andromeda is left to cover?
Don't have an easy way of answering that,
DCD
Rohit,
readout complete.
Galaxies don't have sharp edges, so the disk keeps going for a long, long way. But I would say that we have covered something like half the bright part. But not just tonight, not just last night and tonight, but we also targeted this region in 2022, so a year ago. I would say something like a half of the bright part of Andromeda's disk.
Exposure complete.
Rohit, do you want to say a little bit to the group about what work you've done? Introduce yourself.
Hello everyone, I'm Rohit Raj.
DCD
I'm
readout
an
complete.
attachment and I was working with Raja during summer, and I am working all the time, like from a year. And I was using the same like splash data for the northern part of disk till now to compare it with DESI instrument, which is a different kind of instrument which was used to survey the M31 earlier 2 years ago. So I was just comparing these two surveys and which one is better in which region and what's the difference. And I was also a primary mentor during summer for the SIP. So I was working with 4 other students to do this research during summer.
Thanks, Rohit.
It comes back the same for the time.
Worse, I wonder. Could be better with the ACS fix. Let's see. It should pop up those plots soon. Let's see.
DCD readout complete.
So what we're trying to do now is align the telescope. Okay. Don't go too far off. Yeah. Okay, good. So what happens here is you have this metal plate, right? And it has tiny cuts of metal in it. Tiny cuts in it, very, very thin slices cut. We want the light, we want each of these to capture the light of a unique star. We know which star we want. We've taken an image of this part of the sky using the Hubble telescope. this take the Hubble. We could have taken any ground-based telescope as well. In our case, we are using the Hubble telescope images. Once we've identified which stars we want, those stars form some kind of pattern in the sky. We mimic that pattern on this metal plate. And that way, when the telescope is pointed just right, each of these slits is capturing the light of a different star, one of the stars we want to learn more about.
DCD readout.
Now, to do this, we have to point the telescope just right. Oh, beautiful. The image quality is also improved. Yeah. Beautiful. You can see that there are peaks at the centers of each of these. That's what we want. So we could do send moves only probably for this. No, that's okay. That's okay. It was a biggish move in Y, but that's fine. And what's happening here is we are moving the telescope X shift, says X int, sorry, I'm stealing your cursor from Y inst and rotation. That means it can change the X position of the telescope, the Y position of the telescope, that is where it's pointing, and it can also rotate. Those are the three parameters it's controlling. Okay, so the cursor is back to yours. I'm not going to touch it until. This is the, what we're using is something called virtual computing. The letters V and C at the top of the screen. That means this is a computer that's actually sitting on the mountaintop in Maunakea, but I can control it from my laptop. Lara can control it from her desk there. So I don't want to take the,
DCD
if I move my
readout
cursor, it takes it away from what she's trying to do. Beautiful. This is beautiful. You can see. I'm going to switch screens so you can see what Lara is doing. So you'll notice that all those peaks are now centered, all the boxes under X, Y, and rotation, they said no more moves needed, no more rotation needed. So Lara is now changing the mode in which this instrument is going to operate. Right now it was taking images, now it's going to take a spectrum. We had to take the image to make sure the telescope was pointed just right and that there were stars shining through each of these boxes. And I'll show you those. Lara starts a series of 3 20-minute exposures. I'll show you what I mean about things being lined up well now. We took an image basically through this metal plate, and when things are lined up right, there should be stars shining through each of these cuts. And also, I want to go off and measure C, but once you get it started. Okay. Yeah, it's very close. Can I steal the cursor at that point? Yes. Once it comes in? I'm really happy to see good image quality. Looking at that, I would guess it's better than 0.94 that we started with. Probably better than 0.8 even. I'm going to hazard a guess of 0.7, 0.75. 0.75.
Raja,
Yes, Jimika.
will you check the chat?
Oh, of course, just a moment. I'm not touching the cursor, that's why I'm not, but you're welcome to read it out to me.
Oh no, it's one I just sent to you.
Oh. Oh, okay, thank you. All right, I'll take a look at the chat, Jimika. Just a moment. Oh, okay. Oh no. I don't think it's a headset issue. For like 10 seconds.
About like it just kind of happened just now when you were saying that sentence.
Oh no. Not sure how to rectify it except for just let me know. Yeah. Screen share looks good. Okay. Yeah, this is the internet quality should be high. Yeah, because we're of course an observatory where the internet quality is critical for operations. So Jamaican, I think it's something to do with my own laptop being overburdened doing what it's doing. But I think the best stop me as soon as it cuts out.
Okay, I'll do that.
No worries, no worries. Lara, thank you though. So what we're going to go off and do is measure the seeing. And wow, this does look good. And what I'm saying, looks, these peaks are sharp. The width of this base or this pedestal is 4 arc seconds. And based on that, I'm guessing that the full width half maximum is somewhat better than arc second. So we're interactive mode. I'm going to calc C. Oh, that does look good. So I do photometry. I change the outer radius from 20 to 15. Depends within the square. I do a radial profile. 6.8. So it's a little worse than yesterday for this star, at least. What is 6.8? 6.80. You can see that's the full width half maximum multiplied by 0.1185. That's the pixel scale. I'm getting 0.8. It's a little better than 0.75 I estimated, but I'm going to try this for a few more stars and see how this is. They're all a little elongated. They all look very similar. Do a radial profile. This one is 6.92 instead of 6.8. So very similar. Wow, something is frozen now. It's back. Slightly out around. Something is acting up here for me, Lara. When I hit P over here, it's not bringing up the window I'm used to. We try again. Yeah, please. Does it bring up the photometry window? Does it do it for you? Okay. I'm just going to get out completely and start over.
Because it did. There was something by the
Oh, now it's working fine. Now it's working. It's become very slow. That's what it is.
Okay.
That's what it is. Now, this is the same star we looked at before.
Yeah, so see how it's got the little thing like
Yeah, I see that.
and I guess it's like
It's waiting. Yeah, it's still loading. Exactly. So this one is better, 6.33. Part of it is there's focus variation across the focal plane. So 6.33 instead of 6.80 gives me slightly better. 0.75 on the dot. but it's not uniformly that. I see what you mean about that little, you're going too fast, slow down, kind of. Let's look at some spectra again. After this thing quits. There we go. Look at some spectra, guys. Oh yeah, this is what we were going to look at. See, the spectra will appear in how much time? Let's see. We finished 400 seconds out of 1200, so that's 800 seconds to go. That's another 13 minutes. 780, it's exactly 780 to go. And that's 8 minutes. So in 13 minutes, we'll see the first spectrum of this chunk of sky. Literally the first spectrum of this chunk of sky. I don't think anyone else has looked at this before. So what we can do in the meantime is look at this image, and I'm going to zoom in a little bit. And you'll see that there is a square here, and there's a star shining right through the square, and it's pretty well centered, not perfectly centered, it's slightly left of center. And if I zoom out, you'll see that we just took an image through this metal plate, so you can see slits like this. Oops, sorry, that's not what I wanted to do. Let me zoom in again. You can see that each of these slits, you can see a little brightening. Some of them are, this is very easily visible. This one has 2 spots. These are the stars that are, these are the particular stars whose light they are destined to capture, they were designed to capture. And we've aligned the telescope well, so each of them has some light shining through it. Each of the slits has some light shining through it. You can see each of them. This star is quite bright compared to this one. Can you tell that? This one is quite faint. These 2 are sort of moderate brightness. But every slit has a star shining through it. I'm sort of panning my way around the mask. And as I move my cursor, you can see this little red box move. So if I click over here, it will move over. You can see that's how. So I'm zoomed in a lot. If I zoom out a little bit, you'll see that there are many slits. In fact, if I zoom out a long way, you'll see that there's sort of a rectangular pattern of slits because this metal plate is rectangular. I've zoomed out a lot, so now you can't see any detail. But these spots are squares that are cut into the metal at those locations in the sky, there are bright stars, and we use those bright stars for alignment of the telescope and the mask to achieve as close to perfect alignment as possible. So this particular star that we're looking through is probably a star in the Milky Way. It's not in Andromeda. Andromeda stars are fainter in general. Andromeda is quite far away, 2.5 million light years away. But this is the image of a star in the Milky Way. And if I zoom in enough, you'll see the pixels of the silicon detector. You can actually see the pixels here, can you? You can see it's a rectangle, it's a square cut in a piece of metal. So the only light that's shining through here is the light that's coming through this square cut. Black over here because no light is hitting this part of the silicon. It's gray over here because even though the night sky looks dark, it's actually glowing slightly. And then on top of the night sky's glow, you're seeing the light of a star. Any questions about this as we navigate?
Yes, we do have a question. Trenton and Kavika ask, why does the bright star appear to be in a square cut, but the fainter stars from Andromeda appear to be in rectangular cuts?
Oh, that's a great question. That's a great question. And Jamika, how's my audio been doing?
Oh, I sent you a few messages about it. Yeah, it's happened 3 or 4 times, but I don't think we can really do anything much about it. right now, but it's not super horrible. But those of you in the chat, please, if that audio effect happens and you miss something, just let us know in the chat, and Raja is certainly happy to repeat anything that's difficult to hear. So we apologize for that. Thank you.
Yeah, my apologies. My computer's been acting up and time to get a new one. So that's a great question. See, the squares are used to ensure that they have different purposes, the squares and the slits, right? So the squares, these stars in the squares, we are not trying to measure their spectrum. These stars are in the Milky Way. We only want to use them to point the telescope perfectly, or as close to perfectly as possible. So if the telescope is off, let's say in the Y direction or X direction, we don't want to miss it altogether. That's why we create a box that's relatively large. In this case, the box is what's called 4 arc seconds by 4 arc seconds. Just to give you a sense of scale, the full moon's diameter is 1800 arc seconds, 1800, nearly 2000 arc seconds. And these are only 4 by 4. So they're still quite small patches of sky, but we create a box, not a slit, because we don't want to miss the star altogether. We want to be able to make sure that the star is within the slit. Not just this star, there are other stars you'll see. If I zoom out, you'll see there are other stars. There's this one here, this one here. If I zoom out some more, there's probably 8 or 10 of these across the mask. Zoom out some more. So you can see 2 over here. If I scroll to the right, you can see there's a few more to the right side. Where are the right side ones? You'll be obvious when you see them. 1, 2, 3, 4, 5, right there. These 5 are on the far right. And then on the far left, we have only 2, I think. Let me just click here. Just those 2, these 2. Right. Oh, yeah, there's a third one where the letters pan appear. So these 3 on the left, 5 on the right. And so in each of these, we want to make sure that the star that's intended for them are within it, because if the star is not inside it, we don't know how far off it is. So we do a coarse alignment to get the star inside the box, and then we do fine alignment to make sure the star is right at the center of the box. Now, why don't we do that for the rest of the targets? Why do we cut slits for them? For the rest of them, for the science targets, these are called alignment stars. Everything else is a science target, everything that we're trying to measure a spectrum of in Andromeda. Oops, sorry, I want to zoom in now. For the science targets, we want to minimize the light of the surroundings. So we cut a slit that's just wide enough to include the light of the star. Kavika and Trenton, does that make sense? Zoom out just a little bit. You can see that if I zoom in on this, you can see that the blob, that's the star, and the slit are about the same width. You can barely make out that. You can just sort of see the circular patch that the star creates. I'm going to zoom out and show you a slightly brighter star so you can see this a little better.
Raja,
Yeah.
Trenton and Kavika have a comment there in the chat saying, I think so. So it's a wider cut to allow more of the spectrum to come through?
Oh, why is it wide in the X direction?
Not sure. Trenton and Kavika, could you clarify your question, please?
Do you mean why is it wide in the horizontal direction?
Yes. Why is it so wide?
In the horizontal direction, that's a great question, because what happens is, if we look, I'm going to zoom in, then I'll explain exactly why. So you notice that the slit is narrow in the vertical direction, but wide in the horizontal direction. So when we get the light of this star over here, not only are we getting its light, you can see that its light is sitting on a pedestal. It's getting the glow of the Earth's atmosphere is also hitting that part of the slit. So if we didn't make it extended like this, if we had just made a small square like this, we'd be getting the light of the star and the glow from the Earth's atmosphere together, mixed in together. By making this long, we can look on the star and off the star and correct for the effects of the Earth's atmospheric glow. In other words, we measure this part of the spectrum, and we measure the spectrum from this part of the slit, and that is almost pure Earth's atmospheric glow. And then we subtract that off from this part, and what we are left with is the spectrum of the star. So we do this simple differencing to isolate the light of the star only, to remove the effects of the Earth's atmospheric glow. This is a great question, Trenton and Kavika. I really appreciate it.
Thank you. They say, got it. That totally makes sense. Yes, awesome question.
So we have it extended in X, but not extended in Y. Also, if we were to extend the slit in the Y direction, that would affect the fineness of the resolution of the spectrum, how finely information is isolated versus blurred out in the wavelength direction. Turns out that we can't afford to make this wide in the vertical direction, because our final spectrum is repeated images of this slit. And the wider we make it, the more coarse the resolution. You'll be able to see that in just a minute. In fact, in about 120 seconds, in 2 minutes, this will have counted up to 1200. And at that point, we'll see our first spectrum. And I'll show you what I mean about when you get a spectrum through those square boxes, the spectrum is quite blurred out. When you get it through the slits, it's nice and sharp. So I've asked Sunny, he said he won't come tonight. He said he'd try to log in on Monday. I told him that he's also welcome to come on Monday night, since he was so keen to come tonight. Sunny is one of the high school students from Maunakea who is interested in astronomy, whose family happens to be in Waimea this weekend. So you can see this is counting up in another 60 seconds, another minute. This would have, you can see where it says exposing, that means the silicon device is continuing to collect light from the sky. And we gave it an integration time, a total exposure time of 1200 seconds. That's 20 minutes. For the young uns in there, 1200 is 60 multiplied by 20. 60 seconds make a minute, so that's 20 minutes. And in another 30 seconds, you'll hear the voice. You should hear that in your audio, say exposure complete. And then this will go from exposing to reading out. It'll then read out the silicon device. It'll read what information it collected during those 20 minutes. That's what will be displayed. That's what we'll talk about next.
Exposure complete.
You guys could hear that, right? Exposure complete, and now it's changed to reading out. And even that reading out, it gives you a percentage, how much of it takes about 40 seconds to read out. So it's about a quarter of the way done with that, 10 seconds. Another 30 seconds, it would have finished reading out. I think it's less than 40 seconds. And when that's done, it will start the next exposure in the sequence, right, Lara? Yes. Number 3? No, number 2. Second one. We're going to do a series of 3 20-minute exposures, total of 1 hour. Almost there, almost there.
DCD readout complete.
So CCD readout complete. CCD stands for charge coupled device. Now it's erasing the CCD. Now that it's read it out, it's flushing it, and it's now getting ready to collect light again. And it started 1, 2, 3, 4. It's going to count up to 1200. This is the next exposure. So we can go over and look at the spectrum of the thing that it just created. So over here is a spectrum. I'm going to zoom out a little bit. Change some of my, oh, there we go, much better. Okay, so I'm going to zoom into this. By the way, oh, look at CCD5, Lara. What is it doing? Anyway, we have a glitch up here. You can see it's not doing what it's supposed to be doing. But that's bizarre. So bizarre. Okay, so what I did want to show you is the Earth's atmosphere glows. Okay, it glows in a very strange way. Let me turn this up for a minute. Turn this up even more. Okay, so the Earth's atmosphere glows, glows intensely, even though, it might look like the night sky is quite dark, especially if you get away from city lights. The truth is, to a 10-meter telescope like Keck, the Earth's atmosphere is actually quite bright. It glows quite brightly. For our human eyes, which are much less sensitive, it may look black, but it's putting out light, and it's putting out quite a lot of light. It's putting out light at very specific wavelengths, and those are what produce this horizontal bar, almost like a barcode UPC symbol in a grocery store. You see every time you buy an item at a grocery store, you see this set of lines that tell the computer some kind of code as to what the price of the object is, what the object is. So that barcode here is produced by the Earth's atmosphere. The atmosphere glows at certain wavelengths. So you have wavelength running along the y-axis. And if I zoom in here a little bit, you'll see that the Earth's atmosphere glows at very specific wavelengths. Whoa, look, we have a galaxy here. What do you see this spot here? This is not a star in Andromeda. It's a galaxy. I'm going to see if I can. Sorry, I've gotten distracted by this. I'm going to see if I can find what other emission lines are available. It's either a background galaxy or it's an unusual star with emission lines, which I wouldn't put past this region of the sky. We might. So we're marching up in wavelength to longer and longer wavelengths to see if there are other. I'm ignoring these very sharp spots. Those are produced by high energy particles hitting the detector. That's not light. Whereas that blob we saw was definitely looked circular, looked like light had gone through the Earth's atmosphere. I don't see anything else, Lara. Going all the way to the top. So it's a single emission line. I wonder if it's H alpha in emission. We are using the 600 ZD grating now, right?
Yes.
And see, it's on the blue half of the spectrum. So it's shorter than 7200. I bet it's H alpha in emission. And sometimes you see stars that, oh, look, you see the calcium triplet in emission. You see very faint. You see that here? We'll change the contrast. You'll see it more clearly. You can really see the calcium triplet right there. I've occasionally seen it, and this is some kind of active star. Its chromosphere is active, so it's very subtle, but you can see it. And now I'm convinced that this is not a galaxy, it's a star. And let's make sure we know what it's. I'm going to scroll down like this. And so at some point, we'll cross a black band. That band is the gap between the upper set of silicon devices and the lower set of silicon devices. We haven't hit that gap yet, but we will soon. So we use 2 silicon devices to capture the full spectrum. The Long wavelength part is called the red CCD, charge coupled device, and the short wavelength part is called the blue CCD. So I'm marching my way down the red CCD. And Lara, this gap here is 6850. Like, you know, this gap, that's the B band. Let's see if I can spot the A band. I'm going to march back up. Let's see if we can spot the A band, just to get our wavelength sense of wavelengths right. I wonder if that's the A band or not the B band. That's the main thing I'm worried about. I think that is the A band, not the B band. So I'm going to march down. Sorry, this is so slow and cumbersome. Yeah, because, you know, at around 7,500, the lines get a lot less prominent. So this is 7,600. This you guys see on Zoom that the light has been absorbed by the star. This has been absorbed by the Earth's atmosphere. So the Earth's atmosphere glows at certain wavelengths. It also absorbs light at other wavelengths. So the fact that it's amidst the night sky lines means it's not the B band. The B band is at 6850. That's at 7,600. So if I keep marching down, we'll cross the chip gap. So this is around 7,200. Then this is a bad column. You see this bright column here, but right next to this column, we saw that bright spot. And I bet that's H alpha in emission. Some of you looked through the solar telescope at Astro Day tonight, in those of you who are in Hawaii and Kona. And you know that the sun's corona puts out emission lines. This H alpha emission line is the same kind of red filter we were using for that solar telescope. There we go, there's H alpha. Beautiful.
Raja,
Yeah.
we have several questions from Jeff. So Jeff says, sorry, what is the x-axis and y-axis of the image you are explaining? And then,
Okay. So y-axis is wavelength increasing upwards, and x-axis is where along the slit we are. So you can think of each of these bands. You can see these vertical bands, right? They're demarcated by these dark lines. So each band is what's called a two-dimensional spectrum of the slit. It's repeated images of the slit, different colors of light passing through this rectangular slit end up producing this sweep of a band. Like the best way to think of this is if I took a point of light and I put it through a prism, it would play out into a line. So if I took a single point, but from the slit, you get multiple points of light make up a slit. Each of them plays out into a spectrum, so you get this band. So what is along the x-axis is the position along the slit, whether you're at the left end of the slit, the right end of the slit, or the middle of the slit. And most of the stars we're interested in, we try to place them close to the center of the slit. You can see this one is at the center of this slit, this is at the center of this one, this is at the center of this slit, this is slightly off to the left, and so on. This one's star is so faint that we can't see it here. Now, when you have spectrum collected through this slit, sometimes a star is really bright, like this is a really bright star. Probably in the foreground, not in Andromeda, but we're going to get its spectrum. Now, this one over here, you'll notice that this band that my cursor is on, this is a spectrum that is of one of the alignment stars, and you can see how blocky the spectrum is. Remember I said that when you take a spectrum through a box, it smears out the spectral information. You can see instead of getting sharp lines like this, you get these blocks, and that's not good for measuring things precisely in the spectrum. But I'm super excited about this H alpha emission line for no good reason. It's not like H alpha emission never happens, but it's rare enough that I get to present you with something rare. Now, Kavika's too young to know this, but Trenton, you probably remember that on 9/11, 2001, during the terrorist attacks in New York City and the Pentagon and Pennsylvania. Shortly after that, there was this this alert system that New York City started called "If you see something, say something." Do you remember that?
Yes, indeed, Trenton says.
Yeah, so we are sort of, my student and I have been thinking about that statement a lot. You know, what does that mean? It means if you see something unusual, report it, right? That's what it means. And we're trying to follow that in our research. We're looking at these spectra. If we see something unusual, we don't want to keep quiet about it. Not because, you know, the reasons are completely different. There we're talking about terrorist threats. Here we're talking about if we don't say something about it, we might miss out on discovering something. And no more emission lines for the star. Now this star has a nice bad column to mark it, but it has no other. These are all cosmic ray hits. These are not. And I wouldn't expect any other emission lines for this star. But these are cosmic rays. Cosmic rays are high energy particles that just travel through space, and when they strike a detector like this, they release electrons. And so the detector gets fooled into thinking, you know, that light hit me at this location, but it's actually not light. It's cosmic rays that release electrons. Wow, the star is very. Oh, wow. Do you see this carbon star over here, Lara? So pretty. This really bright star is definitely a carbon star. These very sharp notches are produced by carbon mixed with hydrogen, carbon mixed with nitrogen, carbon mixed with itself, C2 molecules. This very sharp corrugation that you see here is produced by, this is an unusual kind of star also. You don't see that in the other stars, right? These look smooth, but this one, definitely a carbon star. That's very cool. It's also the really bright star is a carbon star. So I bet it's one of these super TRGB stars. It's about the particular giant bunch.
Roger,
yeah.
Jeff asked, does carbon equal a white dwarf?
Not necessarily. In this case, you can have carbon oxygen white dwarfs. In this case, a white dwarf would be too faint for us to see it in Andromeda. Now, could this be a Milky Way star that's in the foreground? It could be a dwarf carbon star, certainly. But it could also just be, you know, till we measure its velocity, which I can't do by eye here, but once we analyze this, we'll be able to measure velocities. And I can show you how we measure velocities. Where do we have some? I thought I had some things that show, yeah, I have them right here, actually, right behind this. This is how we measure velocities. If we could see the locations of the dips, we could read off a velocity. Like this particular star has a velocity of minus 466. So Andromeda stars generally have very negative velocity. Andromeda is coming towards us. Milky Way stars don't have as negative a velocity. So once we measure velocities, we'll be able to tell whether that carbon star is in the Milky Way or not, or in Andromeda. There we go. That's the window we were looking at. Sorry, this window. And there's corrugations throughout. So it's just that it looks saturated here. So if I were to change the, oh, how did it change that to? You can see these corrugations are still present here. Can you see that? Let me change this a little more. Yeah, you can see that it's not smooth. So this double absorption is produced by sodium, sodium atoms. But I see a lot of, this many notches in a spectrum means it's a carbon star. It's interesting that this very bright star is a carbon star. Oh, so this one, a lot of the atmospheric A band is right coincident with the chip gap.
Right.
Almost exactly coincident. So I can't figure out what this star is just by looking at its 2D spectrum. We'll have to, no, it has too many. You see how it has dark bands all the way across. These are, I think of that as associated with carbon stars, almost certainly. You can see the calcium triplet, 1, 2. See the third line a little bit higher up. There's the third line. So 1, 2, 3, that's the calcium. So when you see such a strong calcium triplet, that must be a weak CN star. That's what that is. But it's high up. It's in probably in that red helium burning sequence, probably very high up in that. This is probably one of the more luminous weak CN stars we've ever found in Andromeda. This was very cool. And the fact that it has such a strong calcium triplet, that's associated with oxygen-rich stars. And when we're also seeing these corrugations, carbon, it's the strange mix of the two these stars. I know, it's nice that we can see it without having to analyze the data at all. Just look at the raw data. Okay, enough excitement. That's the star that has the calcium triplet in emission. I'm just going to zoom out a bit. This is, by the way, this is just 20 minutes with, of course, with a very, very powerful telescope. Keck is super powerful. But just 20 minutes, and we're doing 3 of these, of course. And if you can see this red square, that corresponds to, that's telling you which part of this bigger frame we're zoomed into over here. I can move this by clicking here. I can move the red square over here, down here, or up here. Keep moving it around, and that way we're looking at different parts of the spectrum. There are quite a few other bright stars, and this is what I wanted to see, is if that star is super unusually bright. It's not. There are other stars that are comparably bright. So I bet that's a red helium burning star in Andromeda. And I also bet it's an Andromeda. It's not an M32 because, well, first of all, this mask is off M32.
Yes.
And we never see these in M32 because M32 doesn't have that youth, doesn't have the unpopulated, doesn't have the massive stars in them. I mean, intermediate. I guess these are massive. They're not even intermediate. They're young stars.
Yes.
And M32 just doesn't have any of those. It has a very sharp cutoff to the tip of the red giant branch. So this is the power of DEIMOS, how many spectra we're measuring at once, right? Each of these vertical streaks is a spectrum of a different star. In the old days, you'd measure one star at a time, and it would take literally, in this case, we're measuring 180 or so stars at once. And that's 180 times faster than doing one star at a time. In fact, I'm going to look at, this is BH, M31 SBH?
Yes.
Okay, so I'm going to look at a particular directory here, you guys. Open up a window, and I want to show you a little bit more of the innards of how these experiments get set up. So I'm on my laptop here. If I go to my desktop, and then go to my M32 folder, then go to 2023B, just the semester we're in, and then I have something called DSIM out. And I should have a file called M31 SPH in this case. Yeah. Oh, I don't think I have SPH yet. No, I do. Yeah, you're right. I'm just looking for the dot out. Okay, so we can see that looks very cryptic, but every row is a star. And the things that have 0 in the second last column, these are not science spectra. These are spectra. If it's a -1, 0, and a 1, that means it's used for coarse alignment of the mask, and it's not even, we don't even get a spectrum. If it's got a -2, 0, 1, it means we get a spectrum through these squares, and they're not particularly useful for science, but those are the stars that are used for fine alignment. And you can see that their brightness is in the range 17, 16, 18. The smaller the number, the brighter the star. Okay, so these are bright. Then once we get past this row, now we're looking at the science targets, and you can see, first of all, they're generally fainter. Instead of being 16, 17, 18, these are now 19, 20,
Exposure
21.
complete.
So these are stars in Andromeda, and they have a different numbering scheme. One means the highest priority, or one means that the first list. This number of 100 versus 400 tells you what the priority is. We're trying to get the high priority objects onto the mask, but in regions where there aren't any high priority targets, it puts in lower priority things. So this number that's 100 or 400 is the priority. This number after it is the list number. We have list number. One is the priorities within priorities. List one is the highest priority. Within that, the numerical values are further subdivisions of priority. And then this is list 3. I don't see any list 2 over here. Let's forget what the different lists are. This is a long list, and we can...
DCD readout complete.
What I want to do is actually tell you how many stars we are getting spectra of simultaneously. That's why I wanted to look at this mask. So how many science stars are we getting spectra of simultaneously? So I want to go below this line and count how many there are. So my row number here, if I do a control G, my row number is line 19. And then if I scroll down, this row number here is 210. So 19 to 210, how many is that? 192? Do I do my math correctly? So 210 minus 19 plus 1, because we're counting both 19 and 210. 210 minus 19 plus 1 is 192. So we have 192 stars up here whose spectra we're measuring simultaneously, not counting the alignment stars, you know, that are really only used to align the mass. We get their spectra, but they're not that useful. Any questions? You guys have been blabbering away.
No questions in the chat right now, Rajana. It's been great, all the details that you're sharing and giving us the insights into what you're seeing.
No, and it's completely, I mean, as you guys can see, it's impromptu. I mean, this carbon star, I hadn't expected to see it. I hadn't expected to see these emission lines. So this is what Lara and I would be talking about anyway, whether or not you guys were, we'd be discussing these, we'd scan through the spectra as they come in. We'd look to see if there's anything unusual. And sure enough, found 2 unusual things. Very often, there's nothing unusual. They're, garden variety stars. These stars that I said have carbon in them and they're very luminous. One of my PhD students at Santa Cruz, Doug and I are getting ready to write 2 papers about the discovery of this class of stars. Now, we made this discovery gradually. We didn't know what they were first. We noticed they were unusual. This, in the spirit of if you see something, say something, we kept digging, kept asking questions, and we finally made sense of these things. So we're about to write 2 papers that announce to the world that there are these stars that have this strange mix in their atmosphere. They have carbon molecules and they have sort of normal oxygen-rich molecules. Normal stars have oxygen-rich molecules. They don't have carbon-rich stuff. And exactly what physical processes produce these, we're not completely sure. We're working with some world experts who study the interior structures of stars. This is a couple who are based in Padova in Italy, Leo Gerardi and Paola Marigo. So they are co-authors on our paper, and we're trying to make sense of this. But this is how science works. You discover something, you try to make some sense of it, even if it doesn't make complete sense, you report this to the world, so that if other people have some knowledge and they can add some more context or make some more physical sense of what's going on, they can then contribute. But if we don't report it, no one will know we've even found it.
That is really, really exciting, Raja. That is so exciting. When will we know when the paper is out?
We're going to submit, so Doug's paper, we're writing a series of 2 papers. One reports the discovery of these stars in Andromeda and Triangulum. And Doug's paper is about the discovery of these stars in a third galaxy, in the Large Magellanic Cloud, something that's Lara's favorite. So these two papers will be sent to the journal together. We're calling them paper 1, paper 2. Paper 1 is on the discovery of these stars in two galaxies. Paper 2 is about the discovery of these stars in a third galaxy. You might wonder, why are we splitting them like this? Because we have one kind of data for Andromeda and Triangulum. So we're writing a paper based on that. For the Large Magellanic Cloud, we have a different kind, slightly different kind of spectra, different kind of brightness measurements. So it makes sense to split that into a separate paper. Also, in Doug's paper, we do more of the first paper is more about discovery, and the second paper is more about characterization. So that's another reason we're splitting them into two parts. But Jamika, to answer your question, I would be very surprised if the papers aren't submitted to the journal by the end of this year. It's October. They're putting finishing. I can show you, actually. Why don't I do that? Let me show you what these papers look like. You have to see my scary tabs here. But here you go. This is the discovery paper. And oh, I'm going to refresh my screen. Sorry. This is a piece of software that does typesetting of papers. It's something called Overleaf. And you can see the title of the paper is Discovery of a Weak CN. CN is cyanogen, carbon and nitrogen. This is a type of molecule that we are seeing in the spectra of these stars. The title of the paper is not just M31, it's M31 and M33. So if I go to the top of this paper, you can see discovery of a weak CN spectral absorption feature in luminous evolved stars in the Andromeda and Triangulum galaxies. I'm leading this paper. I made this discovery literally more than 10 years ago, but it wasn't full-fledged discovery. I just noticed something unusual. And then as it's taken 10 years to really completely understand this pattern. And so Doug is a PhD student. He's the second author. Antara is a college student, not at the university yet. She was a high school student when she started working with us. These are the two experts in Italy, Leo Gerardi and Paola Marigo. You'll notice that their names are actually in alphabetical order by last name. B, G, K, M, 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 Q, R, 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 alphabetical by last name. Everyone from the third author on is alphabetical by last name. And that's another way of saying that they've all contributed, but we wanted to be democratic and to all of them and say, okay, your contributions are roughly equal, so you're listing you alphabetically. Doug has done more work than any one of them, and I've probably done the most work on this particular paper. So we write a simple story, a summary of the paper here. But I'll show you what I mean by these corrugations. If I zoom in on this, you'll see this. Yeah, these spectra have these very sharp up and down corrugations. Normal spectra don't have this much sort of up and down. And this is produced by different elements and different molecules in the atmospheres of these stars. So class of stars we're talking about are on the right, weak CN stars. The class of stars on the left, they're bona fide carbon stars. They're rare, but they're not a mix of this oxygen and carbon. They just are mostly carbon. These have been known for a while. They're rare, they've been known for a while. And these are sort of some kind of distant cousin of this that we've discovered. The stars on the right are some kind of distant cousin of the ones on the left. The ones on the left are already rare. The ones on the right, they're not so as rare as they're subtle. And I'll show you what I mean by subtle. Do you see this W-shaped spectral feature here? Looks like a W. People see that? In this pink band here on the left. There are two pink bands, the band on the right pink band in the left panel. You see what looks like a capital W or a lowercase w. Do you see that? Yes? Not my imagination, right? You can see this.
Yes.
On the right, you see a very subtle version of that W. See that? Very subtle. Not as extreme. This drop in the W on the carbon stars have a very sharp drop. You don't see as sharp a drop, but you see a slight drop. This is, we deliberately, right at the beginning of the paper, we show this side-by-side comparison. Carbon stars are very well known, and these so-called weak CN stars that we've discovered. Anyway, zoom out. So this is how papers get written, and you can see the corrugation very clearly here. This is wavelength. This is a carbon star. This is a weak CN star. The weak CN star has less extreme corrugations than the than a carbon star. So this is a carbon star. It has a number, phone number. The weak CN star has a different phone number. These are two different stars. This is a weak CN star. You can see what I mean by these sharp corrugations. This is the gentle W I was talking about. The middle of the W is at 8,000. You can see that here. It's at 8,000. This is a template spectrum for. So we created this plot. That's an automated way of classifying these things. Things that are near the left edge of this plot are weak CN stars. Things that are below are carbon stars. Those are these red points are carbon stars. This is for Andromeda. This is for Triangulum. I'm very proud of this acronym, COMET. Does this look like a head and tail of a comet to you?
Yes.
Mind you, this is, we are plotting two quantities here, two scores, and the stars seem to cluster into these distributions that look like comets. So we were calling them comet plots internally. But what these are automated scores by comparing these stars to empirical templates. So clever me, I came up with an acronym called comparison to. So we could keep calling it. So
wait,
this is where we
Raja,
introduced the acronym.
your audio cut out just as you were explaining the COMET acronym. One more time, please.
Okay, so the COMET acronym stands for comparison to empirical templates. So we are taking the COM from comparison, empirical templates is the ET. But we got a big kick out of this because they look like comets. The distribution of points looks like comet, like a head and tail of a comet.
Raja, on the this overleaf over in the left hand side, is this like LaTeX here? What you're
Exactly.
using, right?
It's LaTeX on the left.
Mm-hmm.
Overleaf is a LaTeX interface. Basically, it shows you the LaTeX. This is where you type in your changes, and it shows you what it looks like on the right. So, for example, I'm just noticing that in this section heading, if I double click on this, it shows me where this thing appears, right? And I can see that this should be a back quote. And then do you notice how this quote is reversed? It shouldn't be like that. So if I now recompile this, this quote will get fixed, where I just changed it on the left. It's still compiling. As soon as it reappears, you'd see it. See, it's fixed now. Or, for example, I was just noticing that somewhere we forgot to give the wavelength here. It says 7800 to 8200. It should say angstroms, and it should have a double dash to indicate it's 7800 to 8200. So I'm gonna, put a comma, backslash. So I'm writing in LaTeX now. And if I do that and recompile, it'll put an angstrom symbol after the 8200. There we go. So you can see how chi-squared is generated in LaTeX. I can show you where that appears. So you write backslash chi for the Greek letter chi, and then superscript 2 will create this symbol. And you put it in math mode, you put it within dollar signs. So this is typesetting. This is basically typesetting in LaTeX.
And then another question, Raja, how are the charts created, like that figure 5 with all of the
These are
data?
using Python. This is using Python code. And it's a great question because, we're offering Shadow the Scientist for people to see what we do, but you often don't get into the technical computational sides of things. So we run a program where we, if Shadow the Scientist is like dipping your toe in the water, we run a program where we teach kids how to swim. We teach the swim stroke. Laura, Heather is asking if 12:30 p.m. would work for us to arrive. Let me check with Jamaica how far a drive is on a weekend. Will Hilo be from Waimea?
An hour and 15, maybe an hour and a half on a weekend with
Okay.
people, maybe not in such a rush, an hour and a half.
Okay. You okay with leaving at 11? You won't get much sleep. Okay.
Raja, we have a new participant, Moea, has joined us, and Moea stopped by our booth at Astro Day earlier today and is fascinated by the idea and says thank you. Welcome, Moea. We're so glad you joined us.
Oh, hi. Hello. Hello. Thank you. Jeff left, I know, but thank you. We've been diving into the details of a paper here, but before that, we were looking at spectra. So you'll notice that in this window on the right, where it is, I'm going to scroll down, D stands for DEIMOS, 1008 is the date. Now you might say, why, wait, it's October 7th, why 1008? Because it always uses the universal time date, meaning the Greenwich Mean Time date. By the time our night started here, it was already the 8th of October, according to Greenwich Mean Time. You have to add 10 hours to get to Greenwich Mean Time from Hawaii time plus 10 hours. So we started the night around 7 p.m. Add 10 hours to that, it's 5 a.m., 10:08. So D for DEIMOS, 10:08. And then this is the frame number. This is frame 71, 72, 73, 74. On a typical night, we might collect 100 and some frames. So a lot of these early frames, all the way up to number 61, were calibration frames where we try to calibrate the different masks, make sure we know what wavelength lands on what pixel. We shine arc lamps through them, neon, argon, krypton, xenon, or cadmium, zinc, mercury. We use different settings for the red mask versus the B mask. You notice these all have B in them. And then the later ones have R in them. And then from number 62 onwards, these 4 exposures we used to align the mask. Then we took 1, 2, 3, 4 spectral exposures. Then we use 5 to align the mask, and we've now taken, so far we've taken 2 spectra, and there's a third one coming up after this. Third one's about to read out, actually, or about to finish and read out. You can see it's almost finished. And that happens, Lara will go to another mask. This is would be our third mask of the night. She'll align it, we'll observe it. Moea, tell us about yourself, please, because I'm trying to attach faces to names from Astro Day. Did you come by our booth?
Yes, Moea stopped by our booth at Astro Day, yes.
Oh, okay. Okay. You're not the human of Luna, are you? Because there was a cute dog named Luna who came by.
I don't believe so.
Okay. No. So, Trenton, you're asking, sorry, whether damages the CCD to shine an arc lamp into the sensor. You know, we control the intensity of the arc lamp and the exposure time to make sure that it is that it's not blasting the sensor. We do typically 1 or a few second exposure compared to a faint star in Andromeda where we're doing an hour or 20-minute exposures. Absolutely, that's something we have to be super careful about. The good thing about CCDs is they don't get permanently damaged. They don't have anything like hysteresis, but what happen is we wouldn't get good readings if the piece of silicon you can think of a silicon device as a series of buckets. And if you fill the buckets with water so much that they're completely full, then it's no longer recording useful information. All it's telling you is the buckets are full. And so we want to make sure the buckets never fill up. And that's called saturation. We want to make sure we're. So I'm not going to touch the detector because Lara's now going to change masks and go to a different patch of sky. Lara, which one is it going to be now? Oh, we can see it here. AI, okay. And this one will have inclined slits then?
Yes.
Okay, we'll be able to see that.
Raja, we kind of have a gray lined box.
Oh, sorry.
Actually,
That's because I was looking at the chat.
Oh, okay.
Now it should be gone. We were discussing this yesterday. This is
DCD
Zoom's
readout complete.
way of protecting privacy. If I were looking at the participant list or the chat, I might be seeing things that not everyone is privy to because people can direct message me. So Zoom grays that out. Now you should be back to seeing my full screen.
Yes, thank you.
Pause.
Okay, we're ready here. You can start your alignment.
Lara, you've never been to Gila, right?
No.
Raja,
Yeah,
could you maybe do a quick orientation for Moea of what we're seeing on the screen? Maybe just a few things?
of course, of course. Maya, we are looking at the controls of the of the instrument that measures the spectrum. That's what we're looking at on in both windows here. We're looking at, these are controls that tell us what kind of element, optical element, is being used to split up the color, the light into the colors of the rainbow. That's set by this thing called grating. Oh, Lara, should I be not using? Cursor's yours. Cursor's yours. I won't touch anything. Okay. So the thing that says slit mask. So Lara's controlling the instrument now, so I won't move anything.
DCD readout complete.
At some point I want to go to the alignment box, though. But the two windows you see here are the controls of the instrument that collects focused light from the telescope and splits it up into the colors of the rainbow. The big box on the right guards against the instrument bending under its own weight, and the smaller box on the left, slightly smaller box on the left, controls what the exposure should be, what kind of prism / grating should be in there, which metal plate we want to look through. We look through metal plates like this. So each metal plate has a name and number. The one we're using now is called M31SBAI. You see that under slit mask. Things like that.
Exposure.
The exposure time is set where it says integration, in parenthesis S, integration time in seconds. That's under detector control. You can see mechanism control, detector control, and DEIMOS FCS control are the three main things here. But I'm going to quickly go to a different window. Okay?
DCD readout complete.
Okay, so in this window, we are, oh wow, beautiful, beautiful. We are looking at these peaks. That last one is wonky. Something's going on there.
Yes.
Yeah, and oh, beautiful. So we don't even need to move. Seeing has gotten slightly worse. So in this one, we are the window you're looking at here. We're using it to make sure that the telescope is pointed exactly right. Are you already back to restored to the 7200? Okay, got it. I'm just going to go back to this window and can have the cursor again. Okay, yeah, there we go. It's almost at 7200. So Lara's starting a series of 3 20-minute exposures, but it waits for the instrument to perfectly lock on first before it starts. So you'll see in light blue at the top of this window, it says seeking. Correction status seeking, FCS status seeking. Once that goes to tracking, which will happen soon when this green box enters into that little pink, that green solid box enters into that pink open box. Once that happens, that means it's completely aligned and tracking, both in the spectrograph and the telescope. So once that happens, you'll see the off-target thing will say, let's say tracking, to change its color to green. So this is all very fine controls of something that's huge, something that's the size of a room. You can see the green box is a lot closer to the pink open box, but we want to wait for it to enter that. At that point, we know things are well aligned. So one more iteration, and I think it should be ready to start. And it will automatically zoom in once the green box gets closer to the pink. They're overshot. You see the green box went a little bit too far beyond. But again, it says seeking, but I think within a few seconds now it'll start tracking. How is our overall timeline going for the night? There we go. Now it's changed to tracking, on target and tracking, where it said seeking and off target before. And now the exposure starts counting up in the progress bar in the lower left, you see starts counting up. Okay. At the end of this the end of this mask, or overall at the end. Okay. Okay. And 33. I see. Yeah, I think the seeing is degraded a little bit, just tiny. Oh, Heather is written back. Let's see. So.
Raja Moea says, thank you for your time. Thank you, Moea.
Bye, Rohit.
We hope you can join us again, Moea. Our sessions are constantly updated when we have new ones, so please feel free to check out our website. I will drop the link in the chat, and if you got one of our cards today, then of course the QR code in the back goes to our sessions.
Viveka, what's the name of the hotel in Hilo that we went to last time as a group?
It was the Naniloa by the
Naniloa. Okay. And the restaurant had some onomatopoeic name, with some repeating word.
Hula Hulas.
Hula hula. Okay. I'm still thinking about hula hula and trying to watch the Sunday NFL games there tomorrow. My team is playing. What time of the Niners playing? You can see it on my screen. What time are the Niners playing tomorrow? Where are the Niners?
Yes, they're playing the Cowboys.
That was okay. So they're playing the Cowboys. That's right, and they're playing the late game. So 2:20 p.m. tomorrow. They're both strong teams.
Roger, we have another session at 3 a.m. So will you all be continuing the work that you're doing right now at 3?
Exactly this. I don't know how many people will join. I'll certainly connect. And Jamika, will I be able to record?
Yes. We can chat about it as soon as we finish this session, right after I end the recording, and then we'll get you connected so you can control it.
Okay, perfect. If necessary, I can start the Zoom call now, even for that one, and just, unless it times out, I don't know if it times out.
I'm not sure either.
It might time out. I've noticed if there's inactivity for a certain amount of time, it'll think the time out.
Okay, so we'll just make sure to get you into the Shadow Zoom account before, just to make sure you can start it when you're ready.
That would be the best way. I can start it from the Shadow account.
Yes, exactly. Oh, and Raja, I wanted to say, I forgot to read this. I apologize, Emilio. Emilio shares that they used to be a part of a small, I asked Emilio if they were a part of an astronomy group. Emilio said that they used to be a part of a small group, but not anymore. In the south of Switzerland, where I live, there actually are a few associations and observatories, and maybe like the main one for solar observation in Locarno, because I asked if there were, other clubs in the area, because we certainly would be interested in doing sessions with them or for them, and that is
For
what
them,
Emilio
with
shared.
or for.
Yes, thank you for sharing, Emilio.
Oh, that would be great, Emilio. We're trying to get scientists and just professionals, not just scientists, professionals around the world, participating in this. We just want to make it easy for them to share their work, and Jamaica's done so much work to facilitate this, but we want to make it plug and play for any scientists or any professional who want to be shadowed. But obviously, kids are interested in astronomy, but they're interested in 500 other things, and we want to offer all of these things as options as a way to demystify them, as a way to make them more transparent as to what kind of work goes on in these fields. So if you are passionate about the work you do, and you want to serve as a host for these shadow sessions, they don't need to be 2 hours long like this one. It can be an hour long, it can be 45 minutes long. We'd love just please get in touch with us. Look at how strange the FCS worm is. It's very tight, but it's not at zero.
In the last few minutes of this shadow session, I'd just like to say thank you all for joining us. And in your confirmation email at the bottom, there was a link to a follow-up survey. We would certainly appreciate you taking about a minute of your time to give us some feedback, so that we can help to, that your feedback, of course, will help us improve the participant experience. So we would certainly appreciate that. Raja, any closing words in these last 2.5 minutes?
It was so special today to go to Astro Day and to say, here's Shadow the Scientist, and we're going to do it this evening. It's so, normal days, I would say, okay, next month we have a, shadow session coming up. It's a whole different kind of connection than to say, tonight at 8 p.m. we're going to do this, please come. And I love that we were able to do that today. Jamaica, thanks for letting me tag along with you for Astro Day. It was so much fun.
Absolutely, of course, Raja. Trenton and Kavika say, thank you all so much for taking the time to host this. Kavika loved it, and we'll look forward to future sessions.
Please join us, Trenton, Kavika, please join us. You'll see our calendar. We do this often enough. And, if Kavika School wants to get involved, we can absolutely do that. This is to really raise awareness among children. So if their teachers are interested, Yeah, happy to do it.
They said that would be amazing.
Yeah, I'm reading the chat now, even though it's blocking
Okay.
part of your screen. Thank you.
Yes, Amelia says, brilliant idea to share the professional side of astronomy with non-professionals. I totally agree, Amelia. I've learned so much.
I think I'm going to stop the recording here. And is that okay, Jamika, if I do that?
Absolutely, Raja. Absolutely.
It's
Thank
just-
you, Trenton, Kavika, Amelia,